Welcome, welcome, welcome to our 6-part episode on SAT Math. The first class of this mini-series begins now. We're going to cover essentially 2 years of mathematics, or more. Algebra 1, Algebra 2, some geometry, some trigonometry, in 6 different episodes. Let us tell you a story. We're going to build up from the basic fundamentals to harder and harder concepts, covering everything on the SAT math section of the exam. It's essential you know all the math concepts for the SAT. There is no substitute. No other tips, tricks, and techniques will do as much for you as filling in the gaps in your knowledge and making sure you have a complete mastery of SAT math concepts. So sit back, let us tell you a story, and let us help you improve yourself. In Class 1, we will introduce the Heart of Algebra section as it is defined on the SAT. That basically includes linear functions. How do I start with points or a slope and a point and create the equation of a line? How do I graph that line? How do I interpret that line? How might I evaluate or solve that linear equation? How do I extend that to multiple lines, a system of linear equations, and solve that? Or even a system of linear inequalities and begin to solve and graph that as well, or even absolute value linear equations. That's essentially in total what we're going to cover. We begin with the Cartesian coordinate plane, where every point is defined with an x and a y coordinate on our xy axes, our Cartesian plane. We begin with the concepts of distance, midpoint, and slope. So let's jump right into it. What is distance? Well, distance we can define by our distance formula. D equals the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. And boy, that's an ugly formula. Most of you will forget it a day later. Okay, it works, but essentially if you think about it, this is the Pythagorean theorem. If I have any 2 points on a Cartesian coordinate plane, I have an x2 minus an x1, call that B, and I've got a y2 minus y1, let's call that A. By the way, the x and y Cartesian axes are perpendicular to each other, so A and B form right angles, which means our distance is essentially the hypotenuse of a right triangle. We call it D, but in Pythagorean's theorem, we might refer to it as C. A squared plus B squared equals C squared for the right triangle. Suppose my first point here was something like 5, 4. And then my next point over here would be 1, 1. What do I know? I know the difference in y's is my y2, 4, minus my y1, which is 4 minus 1, or 3. That's one leg of my right triangle, A equals 3. The difference in x is 5, x2, minus x1, which is 1 here, is a distance of 4. My b, the other leg of my right triangle in this case, is 4. My Pythagorean theorem simply works out to a squared plus b squared equals c squared. So what do I get? I get 3 squared plus 4 squared equals some distance, we'll call that c, my hypotenuse of the right triangle squared. Well, c equals the square root of 9 plus 16. That's 3 squared plus 4 squared. C equals the square root of 25, which is simply 5. Okay. One thing to note is that your Pythagorean triples, which are most commonly known as your 3, 4, 5, and 5, 12, 13 triple. There are infinitely many of them, 8, 15, 17. I can go on and on and on. But these are the two you really want to know for the exam. If I see any ratio or scaled proportion of 3, 4, 5, for example, and I'm given 2 of the legs, I can calculate the distance between those points. If I have 3 and 4, I immediately know the distance between them is 5. Or if it were 6 and 8, I know the distance between them is 10. And same thing for the other triples, which help us very quickly, without a calculator, calculate some distances for the exam. Next concept, midpoint. Well, we know on a number line, the midpoint is the point exactly between 2 points. Mathematically, we calculate that as the average of the 2 points. Well, all a Cartesian coordinate system is 2 number lines, one vertical, one horizontal. And if we want to find the midpoint, that is the x and separately the y coordinates that are the midpoints, well, we do it the same way. We just calculate the average for the x's and the average for the y's. Well, how does that work? Let's go back to our original 2 points here. I want the midpoint right there. What is that going to be? Well, that's going to be x1 plus x2 over 2, the average of the x's, which in this case is 5 plus 1 over 2, comma, y coordinate. Don't forget, your midpoint is an xy coordinate. It's not 5 or 10 or some linear scaled amount. Let's look at the average of the y's. The y's is 4 plus 1, and we're dividing by 2 because there are 2 of them in the average. That means our midpoint is essentially going to be 5 plus 1, 6 over 2 is 3, comma, 4 plus 1, 5 over 2. That is the point that's exactly in between the 2 points given in our triangle, on our hypotenuse. Exact. Okay, what about slope? How exactly do we calculate and interpret slope? What is slope? This becomes a very important concept in linear functions and equations. We typically define slope for a line as a constant, m. And the reason it's constant because a slope, unlike any curvy line, doesn't change. Notice at this point, I've got a rise over a run, which is our slope generally. That's very different, say, at this point, where our rise over a run is here, and here it might be very different indeed as well, right? But a line always has that same rise over the run. It's essentially, I have a line, and my change in y, that is my y2 minus y1. I'll use the delta symbol, not a triangle. It means the Greek letter delta, which means change. Delta y divided by the horizontal change, the delta x. That's how we calculate our slope. Okay, so let's see that in action. What would the slope be for the 2 points shown up above, 5, 4, and 1, 1? Well, in this case, it's going to be y2 minus y1, 4 minus 1 divided by x2 minus x1, which is 5 minus 1, and that slope then becomes 3/4. So the correct slope for the example shown above between the points 1, 1 and 5, 4 is 3/4. Note that's a positive slope, and it's a very important concept, whether that slope is positive, negative, 0, or undefined. Let's look at a few examples of that for a couple seconds. If my line is up to the right, as shown here, it's a positive slope. So up to the right is positive. Down to the right is a negative slope. Horizontal slope equals 0. Think about it. Your change in y on a horizontal line is 0. That point and that point and that point on a horizontal line all have the same y. So y2 minus y1 is always 0. Well, what about if my line's vertical, on the other hand? What do we do in that case? Suppose my line goes directly up and down. At that point, the x values are the same for every line, and my change in x is 0. But that's a problem, because that means I'm dividing by 0. My delta y over delta x becomes some number, call it n, divided by 0, which, as you might know, is undefined. We can't divide by 0. It doesn't make sense. So what do we do in that case? Well, we still have an equation for the line. It's just x equals whatever the value is, but the slope is undefined. Now, what happens if my slope is positive and it becomes a little flatter? What does that do to the magnitude of the slope? Well, it becomes smaller, closer and closer to our horizontal m equals 0 slope. It might become fractional, a 1/2 slope, for example. And what happens, or what makes my slope very steep? Well, that m value gets much bigger. It might become 3, 4, 5, 10. And those slopes would therefore look a lot steeper than the original one shown. So it's good to get a sense of the slope, what positive, negative, horizontal, zero slope is, and how it changes the line or the graph as the magnitude of slope changes. Okay, now that we understand the concept of a slope, how do we find a linear equation? What's the approach to do that? Well, to start, I need to have 2 points, as we saw when we calculated the slope in our earlier example, or 1 point and a slope. Let's start with the case of 2 points. Suppose I had the point -3, 2, and the other point was, let's just say 10, -2. So how do we go about finding the linear equation? Well, first is we're going to try and find it in terms of our slope-intercept form. There are 3 forms of a linear equation: slope-intercept, point-slope, and standard form. Students are probably most familiar with the slope-intercept, which is your traditional y equals m, our constant for the slope, x plus b, where b represents the y-intercept. So how do I take advantage of that with the 2 points? Well, the first thing I'm going to do is find my slope. Between these 2 points, how do I get that slope? We know how to do that. M equals y2 minus y1 over x2 minus x1, which is, in this case, 2 minus 2. And by the way, I could choose either point to be my x2, y2, or x1, y1. I just have to stay consistent, okay? So my x2, x1, well, I have to use this as my x2 then, minus 3, minus my x1, which is minus 10. The result for the slope here would be 2 minus or plus 2, which is 4. 2 plus 2 is 4. Minus 3 minus 10, which is minus 13. The slope between these 2 points, or the line that passes through these 2 points, is minus 4/13. So we know it's relatively flat, and it will be going down to the right, okay, just by knowing the measure of the slope. Now, how do I take advantage of our slope-intercept form, y equals mx plus b, to calculate the slope in this case? Well, I'm going to set up my equation, y equals mx plus b, and I know the slope. I'm going to plug that in. That's 4, or negative 4/13. Y equals negative 4/13 x plus b. Well, I need to solve for b. How do I get that? Well, I have x, y points, minus 3, 2, and 10, negative 2. I can choose to plug in any of those points for x, y. And it doesn't matter. It could be any point on the line. So let's choose 10, negative 2. If my x value is 10, that's minus 4 times 10 over 13. My y value would be negative 2. And I would solve for b in the equation at that point. So let's add 40/13 to both sides. B will equal minus 2, which is minus 26/13, expressing it as a fraction with a common denominator, plus our 40/13, which we add to both sides. The result is 40 minus 26 is 14/13. That's the value of b. My resulting equation is going to be y equals minus 4/13 x plus 14/13. And not pretty with all the fractions, but that's the equation of the line that passes through the 2 given points. We started with 2 points, which is what we need to find a linear equation. We calculated a slope. We took the slope and another point that lies on the line, and we calculated the linear equation. And that's one way to find the linear equation. Okay, now that we know how to find the linear equation, how do I graph that line in slope-intercept, or y equals mx plus b format? Fortunately, this format makes it easier to graph. The slope is indicated by that constant m, and the y-intercept, that's where the graph crosses the y-axis, is indicated by that constant b. So let's take a look at a couple of examples and see how we would go about doing that. Sketch the graph of each line. Y equals 1/4 x minus 1. Well, what is the minus 1? That's equivalent to our plus b. That's our y-intercept. So minus 1 on the y-axis right there is where I plot my y-intercept. The slope is going to be plus 1/4. So it's going to be going upward to the right. And that means my change in y is 1 for every change in x that equals 4. So change in y is 1. Go up 1 for every 4 I go right in x. And then going the other way, it would be the reverse. I go -4 and -1. And now I can connect those lines. I essentially get that line. Poorly drawn, I apologize, but that's how it would look. Let's try a couple others. Y equals minus x plus 2. So I'm going to have a negative slope. This is going to be downward to the right. And I'm going to have a positive intercept at 2. My negative slope, it's not shown, but that's a -1 for m. M equals -1. That means for every x I go over, I go down 1 in y, and so on and so forth. So these are 1-by-1 grids, so I'm moving just to every corner of the grids, and when I connect those lines, that is my graph of the line. Let's try a couple others. Y equals x plus 1. That's going to have a y-intercept at plus 1, and it's going to be a slope of plus 1. Again, the 1 coefficient is not shown, so this is going to go up 1 for every 1 it goes over. It's going to look like that approximately. Y equals 4/3 x minus 4. Okay, this is going to have an intercept at -4. It's going to have a 4/3, so an upwards positive slope, which is going to go up 4 for every 3 I go over in x. So I go over 3 in x, I go up 1, 2, 3, 4 in y. Over 3, up 4, and I can begin to graph my line. Then I just merely connect the points. Let's try another. Y equals minus 3x minus 3. So it's going to intercept the y-axis. That is at x equals 0. It'll be y equals -3. And it'll have a slope of -3. So it's going to be downward to the right, which means I go over 1 positive in x. I must go -3 downward. Go 1 to the left negative in x. I must go up 3 in y. And continue that slope, graph the points, and I could connect them and see my line. Y equals 4. How do we think about y equals 4? There's no x there. There's no slope. Well, that simply is at every point on my graph, the y value must equal 4. That's just a horizontal line. M equals 0. You could have thought about it as y equals 0x plus 4 and just simplified it to y equals 4. It's a horizontal line with slope 0. But what about the case I have of x equals 1? That has no slope. I can't put in 0 or anything for the m, but I do have an equation because at x equals 1, we know every point on that line has an x value of 1. And then I can connect my vertical line at that point. So there is an equation, even though there is an undefined slope. Important thing to take away from this is when you have y equals a constant, some numerical value, we'll call it a constant k, you have a horizontal line at that k value. Anytime you have an x equals a constant, you have a vertical line at that x value for that constant. Students often mix those two up, so be careful of that. If we go the other way, you might ask, how do I find the equation of the line from the graph? Well, let's see a few examples of that. If I look at graph 1 here, I have a y-intercept of 4. That's going to be my b value right there. And I have a slope. Looking at it, I go down 1, 2, 3, 4, and over to the right, 1, 2, 3. So that's a change in 4 on the y and a change in 3 on the x. There's actually -4 on the y because we're going down to the right. So that's going to be a negative slope. Okay, so my slope is minus 4/3 y equals minus 4/3 x plus my b value, which is 4, plus 4. That is the equation of this line shown in the graph in y equals mx plus b format. Let's look at number 2. Y equals mx plus b, and I can see my intercept is at 0, so b equals 0. And my slope, again, it's negative, and I'm going down, it looks like 5 downward to go across 3 in x. So y equals minus 5/3 x plus 0, or that's just simply the equation of the line shown. Let's see a couple others. Number 3, our y-intercept is plus 2. And we're not exactly going through -1 there, so be careful. It looks like the next point that lies on the corner of a grid is y minus 4, x negative 2, which means we're going down 6 to go left 2. That means my slope is going to be 6 divided by 2. So y equals 6 divided by 2. That's my slope. Positives, upward to the right, x plus r2, which is our y-intercept. Or stated another way, or simplified, y equals 3x plus 2 is that line right there. The next one, our b value is 0, 3, so b equals 3. And our slope, again, a good crossing point looks to be right there. So it looks like we're going over 1, 2, 3 in x direction to go up 1, 2, 3, 4, 5 in the y direction, which means our slope is going to be 5/3. Y equals 5/3 x plus 3. And that is the equation of that line. What if, on the other hand, I had a line that kind of looked like, say, something like this? Try and draw it a little more accurately here. And I see I cross a point there and a point there on the two grid line corners. But I don't see any y-intercept. Up to now, we used our y-intercept as the first point. I have no y-intercept. I can see the slope of the line. It's positive, going upward to the right. Okay. And I'm going over 2 in x to go up 2, 4, 6, 8, 9 in y. So my slope, which equals my delta y over the delta x, is 9 up to go 2 to the right. It's 9/2. So I have the following for my equation. Y equals 9/2 x plus b. But I don't see the b or the y-intercept on the graph. What do I do? Well, conceptually, we can do the very same thing we did when we found the equation of the line in the first place. If I have an xy point that's on the graph, I can plug that in and derive the value of b. I do have that. If I look over 1, 2, 3, 4, comma, over 4, my point there is 4, comma, 4. I'm going to plug that back in for my x and my y, and I'm going to solve for b. So what does that work out to? That's going to be 4 equals 9/2 times 4 plus b. 4 equals 9 times 2, or 18, plus b. Subtract 18 from both sides. B equals minus 14. Does that make sense? Let's do a quick common sense check. My b is going to be much lower than sort of -5. It's going to be way down there, maybe down here where it actually crosses my axis. So -14 makes sense. My final equation is y equals 9/2 x minus 14. That's the equation of the line, and I did it without seeing the y-intercept on the graph, so you should be able to do the same. In many cases, linear functions present themselves as word problems. So let's make sure we can understand and interpret those word problems in terms of the basic math concepts we've learned so far. How do we take 2 points, form a linear equation? How do we graph that linear equation? How do we take that graph and work backward to understand and find the appropriate linear equations and interpretation? let's take a look at a couple examples. First things first, note linear word problems will always refer to a constant rate of change. That's what defines a line, that constant slope m. It won't be a percentage change of the current value or fractional change. Given that, you'll be able to recognize in most cases that we're looking at a linear word problem. So let's begin. You rent a bicycle for $20 plus $2 per hour. Essentially, our x variable here is hours. It's time. Our y variable is the entire cost in dollars. So what do we know? It's $2 per hour. That's our delta y, our change in dollars, per unit change in time, which is per hour. And $20 represents the initial, our b, our initial or y-intercept cost. So our graph looks like a y-intercept at x equals, or time 0, $20 cost, and we increase at a constant rate of change of 2. Our equation in this case is going to be y equals 2x plus 20, where x represents the number of hours. How about the next one? An auto repair shop charges $50, that's my fixed fee, plus $25 per hour. That's my delta y over delta x per unit change in hour. Same idea here as before. The equation in y equals mx plus b format is going to be y equals the slope, $25 per hour, times x, plus my constant, or y-intercept, 50. So it's $50 initially plus $25 per hour. What about number 3? A candle is 6 inches tall. This is my initial value. It's the B. And it burns at a rate, a constant rate of 1/2 inch per hour. In this case, we have essentially the height of the candle as a function of time, and our x variable is time. Our y-intercept is 6 inches tall, and it burns 1/2 inch per hour, which means it actually has a negative slope, and it's going down per hour. So what's the equation here? Y equals, our m is 1/2 or negative 1/2 because it's burning per hour. So negative 1/2 t, if t is our time variable per hour or measured in hours, plus my y-intercept of b, which is 6. The equation here is y equals minus 1/2 t plus 6. The temperature is 15 degrees and expected to fall 2 degrees per hour. Here, it's y equals mx plus b. Our m is 2 degrees. It's falling, so that's negative 2 for the slope. And our intercept is 15. So the equation becomes y equals minus 2x, where x represents the hours, plus 15. Okay, number 1, Jimmy's having a birthday party at the zoo. The zoo has fixed fee for birthday parties, plus a fee per person. Often our fixed fee is the b value. The fee per person will usually refer to our slope. Jimmy is told the total charge for 10 people, including himself, will be $97.50. And the total charge for 20 people, including himself, will be $175. Note in this case, we are not given the y-intercept directly. We're not given an initial value at 0 people. We need to determine that. And we can figure that out because, like we saw before, we have 2 points. I have the point 10, comma, 97.50, and the point 20, comma, 175. From this, I can figure out, using our mathematical mechanics, the b value of the linear equation, as well as the slope m. So first things first, I want to set up and understand exactly what my y and x variable represent in the word problem. X, in this case, is number of people. Y, in this case, is dollar charge for entrance to the zoo. Okay? So what is my rate of change? Well, it's going to be my delta y over my delta x, which is 175 minus 9750 over 20 minus 10, which is 7750 divided by 10, or $7.75 per extra person. Remember and think about our slope as a rate of change per unit x variable, whatever that x variable is, people in this case. What's the initial value? Well, we don't know that, but we can figure that out. So y equals mx plus b. Y equals 7.75 x plus b. We know the points. Let's put in 20 and 175. So I can say 175 equals 7.75 times 20 plus b. B equals 175 minus 7.75 times 20, if I subtract that from both sides, which is going to be 155, and that equals 20. So our initial value is $20 fixed fee when there are no people going to the zoo as part of your party. So what's the total charge for 17? Well, once I know that, I know my equation. Y equals 7.75x plus 20, and I can plug in 17 for x and figure the total charge. That total charge is going to be 7.75 times 17 plus 20. And this way we can evaluate the linear equation. And that would be a total charge of 151.75. On the flip side, I might want to know the number of people who could come for $500. So my total y value in this case, or charge, would be 500. And I know that equals 7.75 per person times x, the number of people, plus my fixed charge of 20. In this case, I would solve for x. I'll subtract 20 from both sides and then divide by 7.75. X equals 480 divided by 7.75, which in turn equals 61.9 people. Except we have a problem here. I can't take 0.9 people to the zoo. I can't chop one person's hand off and then bring 9/10 of them to the zoo. That would be bad. So what do we do in this case? We do not round that 0.9 up. Logically, we have to get rid of the remainder, and the final answer is 61 people can be taken to the zoo for a total of 500. There'll be some money left over, but that's not enough to pay for the 62nd person. And we'll see that logic at play in various problems on the exam. Let's continue to expand our knowledge of linear functions. The next topic is parallel and perpendicular lines. Parallel lines are, well, they're denoted by two vertical lines that look like train tracks because parallel lines never cross. If I have an equation, say, in y equals mx plus b format, y equals mx plus b, and let's put a specific equation to it, say y equals 2x plus 5. What line would be parallel to this line? Well, parallel lines, they have the same slope. That means the slope of the line that's parallel equals the slope of the original line. The m's are equal. So our parallel line to y equals 2x plus 5 might be y equals, it must be 2x. It must have the same slope. And then it could be plus 6. It could be y equals 2x with a 0 intercept. It could be y equals 2x minus 1. It could be any intercept. So the line actually might look something like this, and all the parallel lines to it would look something like that as well. What about perpendicular lines? Perpendicular lines we denote by the following symbol where two lines are at 90 degrees or right angles to each other. How are they related on linear functions or equations? Well, they have what we would call the negative reciprocal slope. And that sounds like a handful, but basically what that means is if I want the perpendicular line to a particular line of slope m, it equals -1 over the slope of that line m. Okay? Another way to think about it, if I rearranged it, the product of a line and its perpendicular line equals -1. So let's see an example of what that might be for a particular line. Y equals 2x plus 5. Let's start there again. What is a perpendicular line to that line? That would have a slope of m perpendicular equals -1 over the slope of the line is 2, so -1/2. And that line would be essentially something that would be like that. Now, what would a parallel line to that be? Well, it could be any set of parallel lines. There are infinitely many lines that are perpendicular to the original line. Y equals -1/2 x plus 5. Y equals -1/2 x with no intercept, and so on and so forth. I could have several lines that are perpendicular to that. So we know parallel lines have the same slope, and there could be essentially infinitely many parallel lines to any given line. But what if I wanted the parallel line that particularly passes through a point, say, 1, 1? How would I find that? Let's go back to our original equation before. Y equals 2x plus 5, and I want to know a parallel line that passes through a point 1, 1. There's only one parallel line that passes through the point 1, 1, as we can see. So how do we find that? Well, we again do it the same way we did to solve for our equations before. We plugged in the point we know that lies on the line, and we solve for the missing variables. So in this case, this line here is really just going to be y equals m, which we know must be the same, 2x plus what we don't know is what b is. We don't know what the intercept is, because y equals 2x plus 5 might be the line there. We're going to have a different y-intercept. So I'm going to use the point to help solve for b in this case. So I'll plug in 1 for y and 1 for x. 1 equals 2 times 1 plus, again, we know our intercept is not 5, it's b, and that's what we have to find to get the equation for the line that passes through the particular point. Well, now I can solve for b. Subtract 2 from both sides. B equals -1. The parallel line that passes through 1, 1 is y equals 2x minus 1. This is parallel to my original line, but it passes through the point 1, 1. How do we do the same for perpendicular lines? Again, if I had a particular line, I could have any number of perpendicular lines, but perhaps I want the one that particularly passes through a point. Let's again say that point is 1, 1. So what perpendicular line to y equals 2x plus 5 passes through the point 1, 1? It's the same process. We're going to say our perpendicular line has a negative reciprocal slope. That's y equals -1/2 x in this case. That's the negative reciprocal of 2, the original line slope. X plus, well, again, we don't know what that intercept is, so we're just going to call it b for now. But we do have a point that lies on the line, 1, 1, and we're going to plug that back in for our x and our y. So y equals 1 minus 1/2, x equals 1 at the given point that's on the line, plus b, and we can solve for b. I'm going to add half to both sides. B equals plus 3/2. The equation of our perpendicular line that passes through the particular point 1, 1 is y equals minus 1/2 x plus 3/2. And that's how we find parallel and perpendicular lines that pass through specific points. In those cases, there are only unique lines that pass through them. Up until this point, we've been dealing with the popular slope-intercept, or y equals mx plus b format. Why? Mostly because it's easy to graph. But students should be aware of the standard form linear equation ax plus by equals c, where in this case a, b, and c are the constants, kind of like m and b are the constants in the slope-intercept form. They represent numerical coefficients and or constants. Alternatively, there's a point-slope form of an equation. That basically just takes the slope formula, m equals y2 minus y1 divided by x2 minus x1, and makes the x2, y2 a variable that you can change over the course of the line. The result is you get a linear equation. These all can represent the same line. However, point slope, we generally can do everything we need to do here with our slope-intercept form, and students probably find it more intuitive to work with y equals mx plus b, so we will not spend time on that. However, we will focus today on our standard form in this particular lesson. Why? Because it's critical for the exam. You're going to see a lot of it. And students generally, they really don't understand it as well as they should. So first things first, I want to be able to convert back and forth from slope-intercept to standard form. I want to solve essentially my equation. So let's suppose I had 5x plus 10y equals 20. How might I put that into y equals mx plus b format? Perhaps I want to know what the y-intercept is. Well, notice in standard form, you don't get a y-intercept right off the bat. I want to know the slope. Well, again, in standard form, notice you don't see the slope directly, so I might solve for y in this case, and many students will do that on the exam. So how would I do that? Well, algebraically, I'm going to subtract 5x from both sides. I'll get 10y equals minus 5x plus 20. I'll divide through by 10 on both sides and end up getting y equals minus 1/2 x plus 2. Now I know how to interpret that, or most students would say they do. The slope is negative 1/2. It's going to be relatively flat, downward to the right on my graph, and it's going to intercept the y-axis at plus 2. So we can interpret that and understand that from our previous work. But how do we interpret and understand everything we can, or a lot more than we do, directly from standard form? Can I look at a standard form equation and easily graph it, determine the slope, find the y-intercept, figure out what a parallel and a perpendicular line is between two standard form equations? Well, the answer is yes. Let's first talk about graphing. Suppose we took the equation up above, 5x plus 10y equals 20, and I want to graph it. Well, again, I don't have a y-intercept and a slope, so I'm not piecing it together the way I did with the slope-intercept form, but I can graph it by looking at the x-y intercepts and connecting points. For example, the x-intercept must occur at y equals 0. The equation of the x-axis is y equals 0. So I can solve the equation, the standard form linear equation, when y equals 0. That's 5x plus 10 times 0 equals 20. Divide through by 5, x equals 20 over 5, x equals 4. So I know my line intersects the x-axis at 4. If I want the y-intercept, I always plug in x equals 0. And by the way, these concepts are true no matter what type of function you're looking at. Doesn't have to be linear. It could be quadratics. It could be cubics. It could be, trigonometric functions. You name it. Okay. I'm going to plug in x equals 0 for my y-intercept. So 5 times x is 0 plus 10 times y equals 20. And that means 10y equals 20. Y equals 2 when x equals 0. That means my y-intercept is at 2 right here. I can connect those points, and that's the graph of my line. I know how to graph from standard form. In this case, I'm just finding the x-intercepts and the y-intercepts of the graph and connecting them. And by the way, if you look, you'll notice that's a negative 1/2 slope downward to the right, as we knew from y equals mx plus b format when we solved it, and it has a y-intercept of 2. This is consistent with our slope-intercept form. Okay, great. I know how to graph a standard form. How do I quickly determine the slope? Well, one easy way to sort of identify whether your slope is positive or negative is if they have the same signs for the coefficients of x, plus 5 and plus 10, then your slope is negative. It's downward to the right. If there were minus 5, minus 10, again, the same signs, positive and negative for the coefficients, it's a negative slope. If they were alternate signs, say 5x minus 10y equals some number, 20, we know they have a positive slope. So different signs, plus, minus, or minus, plus, the slope is positive. So I can immediately look at a standard form linear equation and tell you if the slope is positive or negative. Okay? How about figuring out the y-intercept? Well, we actually just did that by plugging in x equals 0. Notice that's true for any function we plug in x equals 0. How do we figure out if lines are parallel or perpendicular given a standard format? Well, it helps to convert that standard format into y equals mx plus b format. We can see the equivalent of m is minus a over b. So it's the ratio of the coefficients of x and y that determine the slope. And we can see c over b represents our little b, which is our y-intercept. So c is not directly the y-intercept, but it is only impacted or affected by the intercept. In other words, it shifts the line up and down, does not change the slope. The ratio of the x and y coefficients a and b, that changes the slope. So if I looked at, let's again go back to say 5x plus 10y equals 20. The ratio of the x to y is 5 to 10. So if I want to find a parallel line, I must have that same ratio. Say 2x plus 4y equals some constant. That line is going to be parallel. Why? Because the ratio of the x to y coefficients is 2 to 4, which equals 5 to 10. It's 1/2. It's the same ratio. So I can quickly check the ratios of the coefficients to determine if lines are parallel. Likewise, in standard format, if lines are perpendicular, they're going to have the opposite and switch the coefficients. Well, what does that mean particularly? Let's start with 5x plus 10y again equals 20. A perpendicular line would be 10x minus 5y equals 20. You will switch the xy coefficients, or at least proportionally, and one you'll change sign of them. The other one you'll not. This is a perpendicular line in standard form to my 5x plus 10y equals 20. Okay? How could I create a different one? Let's say I've got minus 2x plus 3y equals 5. Again, I'm going to switch them around, the coefficients, and change one of the signs. So that could be 3x plus, changing the negative to a positive, plus 2y, switching the coefficients, and then I don't have to adjust the actual c unless I need to figure out a particular point it passes through. This line is perpendicular to the original line. Well, let's just double check that. Can we see that actually in slope-intercept form, which might be more intuitive? Well, if I solve the first line for y, I would get y equals 2/3 x plus 5/3. So I have a slope of 2/3 on my original line. Let's solve y for the perpendicular standard format line, this one here. Well, in this case, subtract 3x from both sides. Y equals minus 3x, and I'm going to divide by the coefficient of y. So minus 3/2 x plus 5/2. I have a negative reciprocal coefficient. So you can see this process does work. They are perpendicular lines. All I'm doing for perpendicular is switching the coefficients, or at least the same ratio of coefficients from x to y and vice versa, and changing the sign of one of them. So that might sound a little tricky, but it's actually pretty quick and helps you determine from standard form whether you have perpendicular lines. So now I can graph a standard form. I can quickly assess the positive and negative slope of a standard form. And I can tell you whether standard form lines pretty quickly are parallel or perpendicular, and I can quickly assess the answer choice and figure out which is which can be very useful on the exam. That leads us to the end of Class 1 Heart of Algebra. We hope you got something out of it, and we'll see you in Class 2 next time.